So first, let me define it, and we will then again see that how is this a limit of the random walk. So this is Brownian motion. And we say that a random variable b of t of a continuous variable is a, so I should say b of t, which is a function of continuous time variable t and takes values. Well, this t I should be considering starting from some point. So without loss of generality, we will say that t is bigger than 0 and takes values in so I think I was lost for a second. So you have a random variable b of t, which is a function of a continuous time variable t, starting from some point, which we will call 0, and takes values in real line. So this is our first example where the values of b of t, they are themselves are not even discrete. They are a continuous function. They take continuous values. And we have the following conditions. If the following are satisfied. So what are those? Number one, you have to have, this is not very important, it's just there for convenience, that you start from 0. Number two, if I take a sequence of times, these are continuous, time is continuous, and I just pick some instances in time, then these differences of the values all of these
Hello, Assalamualaikum.
they are independent.
Hello. Sorry, screen show नहीं हो रही.
Screen show नहीं हो रही, sorry. I have to share screen. Is it showing now? Can you see it now?
Yes, sir. It's visible now.
Okay. So let me then go over what I was saying. So you have a random variable b of t, which is a function of a continuous time variable t. And you have to start from somewhere. you don't go on both sides, you go on the one side. So I just call that time 0. And the values it takes this variable b, even they are not discrete this time, they are also real. So you take values in real line, and you have the following properties which have to be satisfied. First is not that important, it's just that it's for convenience that you start from 0. The second is that if you take the sequence of instances in time, and then you take these differences, then they are all independent. So remember, you are making some intervals. So the difference of this interval and this interval and this interval, they are independent. So all these intervals are independent. Then the last one, which is the most important, which defines this Brownian motion, is if I take such a difference, so I have started at a point S and I move by an interval T, then this difference is a normal variable so this difference is a normal variable with mean 0 and standard deviation sigma square t. So, so you have these normal deviations, and so that means, and this is controlled by this parameter, and one can then have the following properties. Brownian motion. So you have that if b of t is a Brownian motion, with variance sigma square. So the variance of the normal variable is sigma square t, but for Brownian motion, you call sigma square is called variance of Brownian motion. Because if this interval, if this is larger, then the deviation, the variance of the normal step, which you're gonna expect to have, that's going to be large. But that depends on this t. So the inherent property of the Brownian motion itself is described by this sigma. So one should think of it before I go to this property. I was just gonna make a comment. One should think of it like if I consider this Brownian motion, for some unit step, I expect a certain deviations. It can go up, go down. I'm expecting certain deviations. But if I consider a very large step, it's not that it's restricted to this deviation sigma. So let's say this is sigma. And so you're not restricted here. What you expect for large steps, that you can go up, and similarly you can go down. So as you move away, these deviations, they become larger and larger. So you can expect to move very far away from your mean, 0, and come back because you can go to the other side as well. So you cross. So this is just like what happened in the random walk. You can go very, very far away. It takes you a lot of time, but you can go very, very far away from the starting position and then come back again as well and then move away. So that's why the normal variable, which describes the difference of these two values, value here and value here, that deviation is a normal deviation, but it scales with t. But the inherent uh, deviations in the motion, they are described by sigma square. Now for the properties, you can consider these properties. Let me write it again. That if B of t is a Brownian motion, with variance sigma square, then the scale thing is also a Brownian motion, but with variance sigma square is equal to 1. So when you have variance 1, this is called the standard Brownian motion, just like standard normal. So this is very easy to see, because if I consider this variable, the new one, and take this difference, then the variance of this is just gonna, because the variance you get square out, and this variance by assumption is variance is sigma square, so this gives you sigma square t. So this becomes t. That means the new sigma square here is 1, because the variance of this normal step is just t. So variance of the Brownian motion is 1. That means just by dividing by sigma, I can convert any Brownian motion into a standard Brownian motion. So just considering the standard Brownian motion is enough, and you can scale in and scale back. The converse one can do the converse as well. If B of t is a Brownian motion with variance 1, then B of sigma square t is Brownian motion with variance sigma square. So this one can also see very easily, because if I consider B of sigma square t plus sigma square s minus B of sigma square s, then since B by assumption is a Brownian motion with variance 1, so I'm gonna have a normal distribution with variance 1, but the time steps I'm considering are sigma square t. So the time step is sigma square t. But this is, again, this is by definition is equal to, this has to be equal to the if I consider this Brownian motion with uh, standard deviation sigma square, I use variance and standard deviation alternatively. I mean variance. When you consider this Brownian motion with variance sigma square, by definition, its difference, its step is equal to this normal distribution. But it's the same as this. So I have proven this fact. So because of these two facts, one can talk about this property of self-similarity. So what does this say? It says that if you consider a standard Brownian motion B of t. So the standard means that its variance is 1. Then if I define a new variable by these scalings, so what I have done, I have divided the variable by 1 over alpha. So that's scaling the y-axis. And at the same time, I have multiplied, so this is b and this is t. At the same time, I have multiplied t by alpha square. So that's scaling the x-axis. So this is zooming if alpha is greater than 1, alpha mod, then this is zooming in the x-axis and y-axis. So what you get from here is that this guy is also a standard normal. A standard Brownian motion. Because, well, this is quite easy to see. So since B of t is a standard Brownian motion, we just proved that B alpha square of t is a Brownian with variance sigma alpha square. Then the other property says that if this is a Brownian with variance alpha square, then if I divide by this is a Brownian with alpha with variance 1. So this is a standard Brownian. So if you zoom in on the t-axis and zoom in on the y-axis, but you have to zoom in at the square of the y-axis, then the appearance of the graph is same. It it looks exactly same as the original graph. So in this sense, the Brownian motion is self-similar. You see some various these kinds of squiggies, and you have a certain feel about them depending on how big or small these variances are. You zoom in, you expect that there may be some smoothing out, but there isn't. Those things again look exactly same. You zoom further, they again look exactly same. So it's a very, very extremely irregular graph. Actually, because of this property, one can show that it has a defining the derivatives is very, very hard of this graph. It's actually not differentiable at any point. Now, one can talk about various quantities of interest of Brownian motion. And some of the most important ones are one is called the hitting time. By the way, Brownian motion can be used to model random walk, especially when one is interested in keeping track of time. There's a limit of random walk. Obviously, all real phenomena, we don't expect them to be exactly continuous, at least the phenomena which we create, like in physical universe, there may be continuous phenomena, but the objects we study, they are they are discrete. Objects we create, they are discrete. But still, it's many a times very, very useful to take continuous limits and study them in as a continuous process because they are many a times much easier to analyze. So that's one of the main motivation behind Brownian motion. So, for example, one could be studying stock prices and model them using the Brownian motion. So there's a random hit up, down, up, down. Maybe the stock takes a new value every minute, but over a longer period of time, you don't want to keep track of those small jumps. So you can model it using a Brownian motion. So it looks something like that. And you model it with this variable. So in the applications, or one of the most important thing which you can compute is the hitting time. So you start from zero and you have a target value, maybe of your stock, and that's A. And you want to estimate that how long it's going to take to reach that value. So maybe you have resolved that you will start from here and you will sell this stock when it reaches the value A. So this is called the hitting time, and one can say that hitting time TA is time to reach value the first time. So you can hit here, come back and hit again. You're not interested in that. You are asking when do you hit it the first time. So one can write it like minimum of these t's so that b of t is equal to a. So that's the hitting time. And we want to calculate that how is this given. Obviously, this is also a random variable because the whole phenomena is random. So the question is, what is the distribution of EA? So to find the distribution, we start with CDF and then look for the PDF. Now this A can be positive or negative. So let's consider A which is positive. So now let's start with this. Suppose at t, b of t is greater than a, greater than or equal to a. Then probability of this event, that your value of the random variable is greater than or equal to a, I can write it down, I can split it using conditional probabilities and the law of total probabilities like this. That b of t, this event is true, that this is my value of b of t is greater than a, but it could be greater than a with the hitting time being greater than t. So hitting time is the first time it reaches a. And the other possibility is in the condition that this is less than t. Now, if I look at this thing, it says the probability that my value of the variable is greater than a while the hitting time, hitting time of a is greater than t. So if then at time t, b of t has to be less than a. Therefore, this probability that b of t is greater than a has to be 0. So this term goes away and I'm left with this term. Now for this second term which is left, we can write the following. If I look at this b of t, I can split it now. This, why did I do this? This by definition, this is just a, and this is b of t minus a. However, this guy, by definition of Brownian motion, this variable normal variable with mean 0 and wait, just give me a second. Yeah, so it's a normal variable with mean 0 and variance of this thing, whatever this is, sigma square. So doesn't matter what the variance is. The main point is that why is it doing this? The main point is that this probability which appears over here is equal to this probability. So what is this saying? This probability is saying that B of t takes a greater value than A, while T of A is equal to T. So that means if I draw this, there is some time Ta where my variable for the first time had reached the value A. And then at time t, I look at what is the value. So it could have gone up or it could have gone down. And this difference between this distribution is a normal distribution. And since normal distribution is symmetric around its mean, and I know that the mean has to be zero by the definition of Brownian motion. So I have equal probability of being above A or below A. So this probability has to be half. Therefore, we get from this equation probability of T of A being less than T because on this side I have B of T being greater than A, and this term became half. So this implies what I have done, I have essentially computed the CDF of this variable T of A. And what I have found that is equal to this 2 times this. And what is this? This is that B of T is greater than A. Now I know that B of T if I plot it, A, here I'm plotting B of t here. T is a constant at the moment. T is fixed. So this is its distribution. And I have this function phi of A of this is for a standard um, Brownian. This gives me the probability of B of t being less than A. But over here, I have the probability of B of t being greater than A. So this is the probability, this area. And this is just equal to 1 minus this. This is the CDF of normal with variance. So therefore, this CDF becomes this is really the CDF. The T of A, we're looking at the distribution. This of TA. This becomes 2 times now similarly, if I look at other hand, if I consider A to be less than 0, so hitting time where you have to hit that value is less than 0, then you will consider the whole thing with B of t less than A. So then by using the same logic, this becomes instead of greater than A, it becomes less than A over here. So you get under root t. But since the CDF of the normal phi is symmetric, if this is phi of, well, let's put it here. This is A. If this is phi of A, then if I look at minus A over here, this area is same as this area because of symmetry. So that means this thing is equal to 1 minus phi of minus a of under t. Since this area is same as this area, this phi is equal to 1 minus this phi. So therefore, what I have found, wait, yeah, so what I have found is that the CDF, which I write like this, CDF of hitting time is equal to 2 times 1 minus phi. If a is greater than 0, it's a over under t. If a is less than 0, it's minus a under t. So that means it's the absolute value which matters only. So that's the CDF. And to get the PDF, you just differentiate and you get this. So when you differentiate this, you get minus 2 derivative of phi of a under t. So it gives you the derivative of this times the derivative of this guy with respect to time. So it gives you and this is simply the PDF of the normal. So you get a PDF of the normal has a 2 pi. You have t to the 3 by 2, so you get t to the 3. And the PDF of the normal is just this. So you have found the PDF of this hitting time. And what you find is that it is a normal. It's not, it's this kind of a inverted thing. T comes over here in the denominator over here. Now, there's another thing which you can calculate, and that is the maximum of a Brownian motion in an interval. So here it was that you wanted to reach a target. Now suppose you restrict to some interval. So you start at 0 and you wait until time t. And the question is, How far would you go in this interval? So this is, we call it m of t. This is maximum of b of t in this interval. So what this would be? Well, to find the CDF of this, so this is a maximum of b, so I'm not denoting its CDF using the variable is not t, it's x. It's the values which b takes, not the time. So by definition, it's m of t less than equal to x, which is 1 minus probability that m of t is greater than x. But if you look at this thing, what is this probability? So this is the probability that in time t, you will exceed x. This is same as, so what it is saying that you will hit x in time t. So that means that the hitting time, the first time you hit x has to be less than t. These two events are same. So the probabilities are same. So you got this, but this we just computed. And that becomes x over t plus 1. And since we are looking at maximum or minimum, since we were said maximum, so I can remove this. Remove the mode. So now you can compute the PDF. And you are differentiating with respect to x. So you get 2 phi so from this normal, you get a 2 pi, you have a under root t, the normal is 2t. So this is how you can compute the distribution of this. Now I said that this Brownian is uh, The Brownian. Well, Brownian is a bit more general. What one should say is that proof, the limit of random walk is a Brownian motion. You can show it using the mean value theorem. Using the central limit theorem. Uh, I don't think I have enough time to do this. So let's do this next time.